Hello dear friends, in this video we will fully implement the radio control hardware. We will look at the printed circuit board design, functionality and software implementation of the Palyonysh hardware. I've implemented a minimal set of functions, only the essential are included here. Palyonysh is a fairly primitive radio control command transmission device. Despite its simplicity, Palyonysh hardware offers flexibility and easy firmware modification and the addition of new features. Additionally, it provides sufficient connection quality and channel count, making it easy to use for a novice programmer, although I never used commercially available hardware. Judging by the data I reviewed, it's either quite complex or contains a lot of proprietary code that's inaccessible for review. Furthermore, the excessive functionality obscures the fundamental concept behind its operation principles. Existing systems have been developed and used for a long time, and they've accumulated numerous features and code, making them difficult to understand, especially for beginners. Therefore, if you want to understand how radio control equipment works, develop your own, or grasp the basic concept of similar devices, watch this video to the end. For those new to the channel, I'll say that we didn't arrive at this device right away, and we've done a lot of work in previous videos. We studied the necessary microcontroller functionality, implemented and used a variety of code, designed several peripherals, wrote drivers for them, and conducted testing. This is an approximate path we took before implementing this equipment. Our video today is in the center of the diagram. As you can see from the diagram, many of the paths lead to it. Beginners, don't be intimidated. You don't need to watch all of this. Today's video is self-contained, and the information presented in it will be sufficient. I did this to introduce you to the development history, so you will subscribe to the channel and like it. There will be more interesting videos to come.
I recommend watching this video. It explains the hardware implementation of the project and the operating principles of the equipment. I won't show it in this video as I've already covered it all before. Quite a bit of time has passed since that video was published, and I am currently using the second version of Palyonysh, but there are no significant change in the second version that require attention. Here's a brief overview of LoRa's theoretical work. You can watch this video in English with automatic translation and subtitles enabled. This video describes the principle of selecting antennas, a little about antenna theory, and also the principle we used when choosing transmission parameters and command packet length. In this video, we implemented a castellated board and tested the code and circuit. In today's video, we are using Palyonysh with one of these radio module circuits. While you can easily solder a factory-made module into it, it's just as good as a homemade one. Links to factory-made modules are also provided in this video. There are other modules that are pin-compatible with the homemade ones. I recommended watching this video. It demonstrates some interesting testing methods. All the versions of the LoRa drives contain a bug. I found and fixed it using the testing methods shown in the video. We use the LeShay keypad in our command transmission equipment. There is a separate video about it. I think the project would be incomplete without it. However, nothing prevents you from changing the input device. I consider the keypads presents on the equipment an advantage over manufacturer installed modules.
This system works very simple. When you first launch it, you see a welcome page. I click the transmission settings button. From here you can change the frequency and transmission parameters. I showed a video above that explains all these parameters in detail. I also showed how changing these parameters affect the number of transmitted packets. I'd like to point out that when you first launch the sticks, their zero position is either read from memory if you have previously calibrated them, or the current stick position when you turn on the device is used as 0. If you accidentally set the sticks beyond 0 during startup, the cuffed values will be applied, or the ones you saved during calibration. Let's perform a calibration. I'll reset the old values with this button, set the stick position to 0. The springs turned out to be weak and don't return to the 0 position. I'm waiting for shorter and stronger springs. Then I'll turn the device on again. I'll press the calibration button. Now I need to move the sticks to their extreme positions. I'll press the calibration button again, and the values will be saved to flash memory. Now, when you first turn them on, they will be loaded from memory. To begin transmitting, simply press the start button. The screen displays the number of packets transmitted per second. To stop transmitting, press the stop button. In transmitting mode, the key assignment on the keypad changed to this. You can change it by editing the program. It's not that complicated.
Where did the term number of channels come from? Back in the early days of radio control equipment, the control signal was analog. Each command used its own frequency. This number of frequencies the equipment can transmit on is called the number of channels. Now everything has changed. We have started transmitting digital commands, so we can transmit multiple commands on a single channel, but the name remains the same. Similarly, in the Palyonysh equipment we send packets containing all the commands. The packets are sent on a single channel. That's why I use the term number of commands rather than number of channels.
To help explain the program's operating principles, I created this diagram. The diagram shows the functional blocks, which are the parts into which I can logically divide the program. Let's start with the initialization block. In the program, this is represented by a number of functions. These are the STM32 peripheral initialization functions, which we won't discuss here. You can download the project from GitHub and explore the settings in CubeMX yourself. We will focus on the user-defined initialization function below. Let's start with the function that reads the calibration values. How does it work? First, it initiates the ADC conversion from 4 channels and reads the values using DMA. Then it waits 100 milliseconds for several readings to occur. This function also reads the current stick position and sets them as the 0 or center position, which is the point from which stick deflection will be measured. Well, after we have launched the ADC and written the 0 positions of the sticks, we read the flash memory, the area where the calibration values are stored, and determine whether there are calibration values there. If there is a key in the memory, that means the values have already been written there. Therefore, we write them to the caliber value structure. I'll show you later where the calibration values are used and how the ADC works. Next, the function reads the 0 position of the sticks from memory. If there is no key in memory, we initialize the calibration values to 1. Well, what are these calibration values? The hardware uses single byte commands, but the sticks don't deviate exactly plus minus 127 ADC values. Therefore, we multiply the read values by these coefficients to get plus minus 127 units as the extreme stick positions. Otherwise, we won't be able to rotate sharply. Of course, you can add your own functions for calculating command values, but we will discuss how exactly these values are calculated and used later. The keypad has button that, when pressed, will reset the calibration or restart it. This microcontroller doesn't have EEPROM memory like the AVR. Everything is written directly to memory. Next, let's look at the keypad initialization function. The keypad operates using I2C. This function simply transmits the following commands. These commands simply initialize the keypad to the desired mode. I have a separate video on this topic. This function configures the display's operation. I've been using this display for a long time, so there is nothing complicated about it. I am using Ruslan Nadirshyn library. I only made minor change here. Next, the LoRa settings are saved, which will be the default unless you change them in the menu. These are the LoRa chip's transmission settings. Here you can set 433.5 MHz power bandwidth, spreading factor, and error coding coefficient. Next, the menu handle is launched. This simply displays information based on our current state. We'll say something was pressed on the keyboard, and any change will definitely be reflected in the menu. Here everything is mostly related to output, but on the 5th page, that is when the calibration key is pressed. We will run this function every second, but I'll explain that in detail later. And then you can see that there is nothing in the while loop. This is because all processing is interrupt driven. Interrupts can be triggered by various sources, including ADC interrupts, second interrupts, button pressed, or the completion of a LoRa packet transmission. My STM32 has trigger pins that trigger the same interrupt. In my case, these are interrupts from the keypad controller and the LoRa chip. We will jump to this function when the key is pressed, when a command packet is transmitted, or when it's forced from another function. This checks whether we jumped here due to a keypad interrupt or whether we jumped here after a command packet was transmitted. Let's assume we have configured the transmission parameters in the menu and then press the Start Transmission button. After preceding the keystroke, we will move on to this part of the function. We will cover the keystroke handle later. First, we will create a command array. The ADC converter runs continuously. It starts during the microcontroller's initialization. However, after pressing the Start Transmission button, the program begins using the ADC conversion values to calculate commands. In this case, 4 stick channels are calculated here. The commands are also calculated using calibration values that we either loaded from memory when the device was turned on or pre-calibrated. We will later separate the calculation of these calibration values from the ADC operation. For now, just note the context in which the ADC and caliber values are used. Conversion and averaging of ADC values occurs more frequently than packet transmission. We will perform this procedure each time a packet is sent. and the calculated commands will be written to the command array, which will later be transmitted to the radio channel. Please note that the sticks can move both positively and negatively relative to the 0 position. The stick travel in opposite direction may differ, so different calibration values are used for the positive and negative directions. Trimmers and other auxiliary commands are also written here, which are read when the keypad is pressed. Next, the function writes the command array to the LoRa chip's FIFO memory via SPI. After the function starts transmitting, the command array is transmitted to the radio channel. Here, the number of bytes to be transmitted is set, as well as the starting address of the command array in the LoRa chip's FIFO memory. Then the transmission begins. Next, the number of packets variable is incremented. It's used to count the number of transmitted command packets. Every second after the number of transmitted packets is displayed, it's reset to 0. This all happens during a 1 second interrupt. The Palyonysh hardware uses a precision quartz resonator, so the measurement of the number of transmitted packets is quite accurate. As we already know, commands are calculated using values read from the ADC multiplied by calibration coefficients. Let's first look at how ADC values are read. During the initialization in this function, we initiate the ADC conversion on channel 4 using delay. After transferring the ADC conversion values across all channels, we proceed to the callback function, and then the function that calculates the stick deflection is executed. Here's how it works. We average the sum of 151 ADC conversions and convert them to a single byte value. The averaging is simple. The sum of all conversion is divided by the number. The sum is written here. As you can see, we use a 0 value and then shift the resulting number by 3 places. Generally, the ST manual recommends shifting by 1 place. In addition to these accuracy enhancing measures, I followed ST's recommendations for ADC circuit routing. In this video, I showed images from the manual. I recommend watching this video. The ADC1 calc array now contains the stick deviation values. I forgot to mention that we use this variable to display the number of conversions. Again, in a 1 second interrupt. Conversions from the ADC occur continuously from the moment Palyonysh is initialized throughout the entire device's operation. To calculate commands, the average stick deviation values are not enough. We also need to calculate the calibration coefficients. Let's say we press the Start Calibration button on the keypad in the menu. We will jump to the ET-GPIO handle function via interrupt, which will trigger the key press handling function. Then we will modify the structure used to draw the menu page 5. Next, in the key press menu, we will run cal_val. When calibration starts, this function simply writes the extreme stick positions to the structure. It will write every second, so there is no need to rush. Simply slowly move all the sticks to their extreme positions. During calibration, the values of the sticks' extreme positions will be displayed on the screen using the print calib max min function. After calibration is complete, press the calibration stop button. The program will jump to the interrupt handle after pressing the button and call the cal_val function again, but this time with the right parameter, the calculation will then occur. The calibration coefficients are calculated simply by dividing the maximum value of our single byte command by the maximum stick deflection. These values are then written to the flash mem call structure along with the 0 position of the sticks. The structure is then written to flash memory along with the key. When the device is turned on, these values will be read from memory during boot initialization. So recalibration will no longer be required. We have already covered this part. We have covered all the necessary parts to understand how stick deflection commands are calculated. Now let's look at processing a key press on the keypad. The read FIFO reads the code of the pressed key. Then the pressed handle is launched. This handle then modifies the structure depending on where and which button was pressed. The fields of this structure are then used to determine the actions the microcontroller will perform. For example, it will display the LoRa settings menu, the number of ADC conversions, the start of transmission or calibration. After the structure is formed, a handle will launched, which then displays the necessary information on the screen. Also, by pressing buttons while transmitting commands, we can change the trim variables. Depending on the button pressed, we increase or decrease the trim position variable. I won't explain what radar trims are. Any other information you provide can be included here. Command transmission will only begin after pressing the start button. We will again access the new press state key handle. If this button is pressed, we initiate the initialization of the LoRa chip for transmission. LoRa param calc writes the transmission parameters to memory. If we haven't changed them in the menu, the values initialized at startup will be written. As you can see, the frequency, spreading factor, power, bandwidth, and error coding coefficient are calculated here. Finally, LoRa is configured for transmission. All data is written to the LoRa configuration registers via SPI. Only after we have fully initialized LoRa for transmission will we call the interrupt handle again. Let's jump to this part of the handle function, and then you already know what happens. An array of commands will be generated. You already know where all this number come from, and so on. The transmission will continue until the stop button is pressed or the power is turned off. In addition to the interrupt shown, I'll also show the real-time clock interrupt. It's simple. Every second a procedure runs that displays information on the screen. That's all. I think I've covered enough for you to understand the operating principles of the command transmission, hardware, firmware. Now let's test it. Turn on Palyonysh and skip the transmission settings. By default, the receiver and transmitter have identical settings. To achieve the specified 24 commands per second, you need to reduce the spreading factor by 1 on the receiver as well. We want to do that. We will reduce the Palyonysh hardware power to the minimum possible with this firmware. We won't perform calibration. We have already done that. The current values are stored in memory. I'll click the ADC conversion display button. Now you can see the numbers changing on the screen, which means the sticks are working. You can also see the number of conversion 1123 conversions per second. We will be using this receiver, and I'll also be posting the firmware on GitHub. In one of our previous videos, we wrote a command interface for it. I added another command to the command interface and several functions for outputting received LoRa commands. You can explore this in the source code. Today we'll be looking only at the Palyonysh hardware. I showed how to make the antennas used in the previous video. The receiver is connected to the PC via UART. The connection was also shown in the previous video. Now I press transmit. The screen displays the number of transmitted packets. Every second the receiver displays the received single byte commands corresponding to the stick movement. I move the sticks to the different positions. As you can see, everything works. We don't exceed the specified range. The equipment is performing its intended task. The tests have been passed.
The source code above is sufficient for understanding the operating principle of the hardware, but beyond the software there is also hardware that I haven't yet covered. The radio module's circuit has a matching circuit for the source impedance, which is our LoRa chip with a 50 ohm antenna. Matching is achieved at a frequency of 433 MHz, although you can easily change the transmitter's transmit frequency. You will achieve the best range and reliability at 433.5 MHz. And if you are planning to build a completely homemade setup, you will need to choose antennas. I've already done some of the work for you, experimenting with various antennas and based on my experience, putting together a special antenna guide for you. These antennas have shown the best results. I'll point out a few shortcomings of the device right away. Without a battery, Palyonysh can't operate on USB power. This is due to a circuit design error. The sticks don't return to the 0 point. This is due to the either long springs or springs that are too thin. I leave a link to the springs I use. Stiffer springs haven't arrived yet and they still need to be tested. After reinstalling the battery, you need to reconnect the USB charger. This is due to the battery's over-discharge protection. That's all for now. I think we will be looking at and testing the command executor in the next video. Thanks for the watching, subscribe to the channel, like, comment, and see you next time.